Hello class, welcome. In last week's tutorial, we used the frequent terms as predictors and the term frequencies as the values for the predictors to predict the sentiment of movie reviews, positive or negative. So for this tutorial, we will introduce two more weights for the predictor values. One is binary weights and the other one is TF-IDF weight. So let's get started. Well, first we want to load all the necessary libraries, and then we will import the review dataset from last week, the movie one dataset. Well, the movie one dataset has two columns, if you still recall. One is label, one is review contents. So the label is actually factor variables with two levels, positive and negative. So here we use factor to transform the label to factor variable. Well, next we use the iConv. This function could convert between character string encodings. So we want to convert the review encodings from this one to UTF-8. And we use list apply function to apply this function to all the reviews in our dataset. So in total, we still got 2,000 reviews, and 50% of them are positive and 50% of them are negative. Well, next, we want to partition our dataset into training and testing as usual, and we still use our old routine, like partition 50% of the instances into training, and the rest 50% will further partitioned into testing 1, testing 2. Well, testing 1, testing 2 will include like 20% of the instances from our dataset. So still, we need to set seed first, and then we use create data partition function. Well, this function, if you cannot find this function, if you have this kind of error, you probably need to load the library caret again. And we will check the number of rows so in each set. So for training dataset, we should have 1,000 rows, and for testing 1, testing 2, each of them has 500 rows. And the label distribution is all 50% and 50% for positive and negative. Well, next we will create our document term matrix with binary weights for each term. But before we do that, we need to first clean our reviews. Well, we did that in our last tutorial step by step, and also use one row of our code by using the document term matrix function with the additional parameter list. Here we will also show you step by step for demonstration. We will first clean the reviews from training dataset. So the first thing we need to do is convert them into a corpus. And then these are 6 steps we're gonna use to do the text pre-processing to clean them. Well, we first change all the letters into lower cases, and then we want to remove all the numbers that are unnecessary for prediction, and then also remove all the stop words. Well, stop words are those words doesn't have a lot of meaning, so it doesn't contribute much to our prediction either. And the fourth step is to transform all the words, all the terms in our reviews to their stem format. Well, next we will remove all the punctuations and then remove all the white space. Well, now after these 6 steps, we will have a more clean corpus, and then we will use this clean corpus to construct our document term matrix. So here, in order to calculate the binary weight, instead of term frequency, we will include an additional parameter, weighting. Weighting equals to weight bin. So what is binary weights for the terms? So let's see an example. So here is an example, the document term matrix example, calculating term frequency from last week. Those values in each in the cells are the actual term frequencies. So for example, if word 1 appears twice in review 1, the term frequency for word 1 in review 1 is 2. Well, for the binary weight, instead of calculating term frequency, now we will count the term appearance. So, for example, if this word 1 appears, occurs in review 1, we will give the weight 1 to this cell. We don't care like this word, well, it probably appeared twice or 3 times, but we don't care. We only give value 1. So for binary weights in this matrix, the binary weights consist of 2 values, 1 or 0. So 0 means this word 3 never appears in this review 1. But if it does appear in this review 1, it will have a value 1. So that is binary weight for each term that can use this weighting parameter to calculate. So next, let's check the dimension of this document term matrix. Similarly, each row will represent each review. The columns stand for the terms. And let's inspect the value for the first review, and check the binary weight for the first 200 terms. So you can see here the values, the weights are all 1 or 0s. So here we see acid appears in this document, in this review, and actual, actor. These are the only 3 terms from the top 200 terms that actually occurs in this review 1. Well, next we want to remove the sparse terms from this. Let's see how many words we have. 21,000, more than 21,000 terms. So we want to remove those remove the words with higher sparsity. So here we set the parameter equals to 0.95%, which means, for example, if we have 100 reviews, those terms that appears in 5 or less reviews will be removed. So if we have like less number here, like 0, for example, 90%, we'll have less terms remain, which means more terms will be removed from the frequent term collections. So here, let's see how many terms left as frequent terms. So we still got 1,000 rows, 1,000 reviews, but we only have 1,006 columns So only 1006 frequent terms are left as our predictors. And then we save these 1006 terms into train backup words 95 for later usage. So you can see those are these 1006 terms. Next, we want to transform this document term matrix into a normal matrix in order to create the training data set. Well, among these 1006 frequent terms, we want to show you the top 20 most frequent terms. We still use the column means to calculate the average of each column for each term, and then we sort the frequency in descending order. So here, this is how we calculate term frequency back in our last tutorial. Here we just sums up all the ones and zeros and divide it by total row numbers. Well, the average binary weight for the top 20 most frequent terms are 0.6599. And then we want to demonstrate these 20 words in a bar plot. So you can see that film, movie, one, like those words are having the highest frequency, not frequency, have the highest binary weights. Well, next we want to combine the sentiment column with the matrix form to construct our training data set. So this is the sentiment label we have for each review, and this is the matrix we just converted from the document term matrix. And we use data frame to combine these two together. And next, we want to create the testing 1 data frame. Similarly, we will first convert the review from testing 1 to a corpus, and then do the all 6 steps of data preprocessing. Well, next we use this document term matrix to calculate the binary weights for each term from the for the testing 1. But instead of all terms, we select the terms from training dataset. Those those 1006 frequent terms from training dataset. So we only calculate the binary weights for these 1006 terms. The reason, well, like we said before in our last tutorial, is to make the predictor consistent. So in the training dataset, we have 1006 predictors. In testing dataset, we also need those exact 1006 predictors. And similarly, we will combine the label together with this matrix to construct our testing 1. The value in these predictors are the binary weights instead of term weights, because here we also use the weighting equals to weight bin as an additional parameter. So here we also want to demonstrate you the top 20 most top 20 words with the highest binary weights. So as you can see, so for testing 1, one film, movie, like, make, the same terms are also having the highest binary weights values. And then similarly, these are the exact same steps for testing data 2. So we'll skip that, just run it. It may take a few seconds. So let's check. Well, similarly, well, the sequence may be a little different, but still those words are still have the highest weights. Well, next we will do the sentiment classification using the 1006 predictors with binary weights as the values. First of all, we want to build this, the C tree model, the decision tree model. Well, we use all 1006 the terms as predictors and using the training data frame to build this decision tree model. Remember to load this library part before you're building this decision tree model. Well, it still will take a few seconds. Well, after build the model, we will use the testing 1 and testing 2 to evaluate the performance. Here, we will use both confusion matrix to construct the confusion matrix, and then also use the M matrix to output the accuracy, recall, precision, and F measure. Well, we can see that the performance for both testing 1 and testing 2 are consistent or similar, and the accuracy for testing 1 reaches over 67%, and for the testing 2, the accuracy achieved more than 65%. Well, these are the performance using the decision tree model. And next, we use the naive-Bayes model using E1071 from E1071 library. And we still use those 1006 predictors with label as target variable. And the performance, and similarly, we also use testing 1 and testing 2 to evaluate the naive-Bayes model performance. Well, because it will take a few seconds, let's directly look at our output. So here, the precision, the accuracy for both testing 1 and testing 2 using naive-Bayes model improved a lot, almost 10%. Now for testing data 1, we have accuracy more than 75%, and for testing 2, we have more than 73%. Well, besides naive-Bayes model, we also tried the support vector machine classification model from CurlLab, and well, you can also try other models such as ANN or others. And then for testing 1 and testing 2, well, the performance further improved. Well, for testing 2, the accuracy reaches to more than 80%, which is very good. And for testing 1, it is 82%. And the precision, recall, and F measure, they're all above 80%. Well, next we're gonna talk about the another weight called TF-IDF. Well, we'll first introduce the normalized TF-IDF, and then we'll show you how to do unnormalized TF-IDF weights. Well, so first of all, what are the TF-IDF weights? Well, let's first look at an example. Sorry, not this one. Well, the TF-IDF actually consists of two concepts, TF and IDF. TF is term frequency. IDF is inverse document frequency. We will first introduce the term frequency. While term frequency can also be separated into normalized term frequency or unnormalized term frequency. Well, we'll first introduce you how to calculate the normalized term frequency. Well, here is an example. So normalized term frequency is using the number of time of term t appears in a document divided by the total number of terms in the document. So for example, let's check our first example. So for review 1, in total we got 10 words. You need to sum the values from first row up, which equals to 10. And then for the first cell, word 1 occurs twice in review 1. Therefore, the normalized term frequency for word 1 regarding review 1 is using 2 divided by 10. Similarly, for word 2 is 1 divided by 10. Therefore, we will have the term frequency for each term in responding to each review. Well, for the normalized term frequency, if you sum the values from each row up, you will get the value 1. That's why we call it normalized. Well, for the unnormalized term frequency, it is actually our first example. It is those exact term frequency that we're gonna use. And the second concept is inverse document frequency. So why do we want to include this inverse document frequency? Well, there are a lot of terms, even though they are frequent. For example, the movie, films, one, lack, so on and so forth. These words appears basically in each one of the review. However, it doesn't contribute much to distinguishing the positive reviews from negative reviews. So we want to weight down those frequent terms, but scale up those rare ones. So therefore, we compute this inverse document frequency. Well, it can calculate by using the total number of documents divided by the number of documents with term t in that, and use the logarithm, give the logarithm of this value with e as basis. So for example, for word 1, in total we got 7 reviews, right? But word 1 occurs in 1, 2, 3, 4, 5 reviews out of 7. So we will use 7 divided by 5 and calculate logarithm. Well, for word 2, for example here, 1, 2, 3, 4, we have only 4 reviews have word 2. So we'll use 7 divided by 4. Well, after we calculate the term frequency and inverse document frequency, we get the product of these two, and that is the TF-IDF weight for each term t. Well, here we'll introduce how to calculate the normalized and unnormalized term frequency, the TF-IDF, for each term in R. Well, first of all, we quote these steps because we already cleaned our reviews. So we will directly use our step 6, which is the corpus already finishing the text preprocessing. And instead of using weight bin, which is calculate binary weights, now we will use the value weight TF-IDF, which will calculate the normalized TF-IDF TF-IDF index the weights for each term. And then let's check the dimension of this document term matrix. Well, still we will got 1,000 rows, which represent 1,000 reviews, and also more than 21,000 terms. Well, the dimension didn't change, but the value, the actual weights inside this term matrix actually changed from binary weights to IDF, TF-IDF. Well, similarly, we want to remove those sparse terms, also given the value 95% sparsity. So because this step is based on the sparsity, so basically we will still have the exact same 1006 frequent terms. And these 1006 terms will be further saved in this same training backup word 95 variable. And then similarly, we will transform the term matrix into a normal matrix. And then, well, we want to show the top 20 words, 20 terms with the highest TF-IDF weights. So we'll still use column means and sort them in descending orders, and then demonstrate them in the plot. So for these 20 top terms with highest TF-IDF values, we can see the average TF-IDF value is pretty low. It's less than 0.003. So in order to demonstrate them in a bar plot, we will change the range to 0.005 in order to show you the plots. So this is from the training data set. You can see, okay, still like the movie, story, comedy, action, life. Well, movie is still like placed in the first place. However, like film, and other like make and other words, is not here anymore. So the comedy, action, life, bad, these words are actually placed in top. And then we will combine the labels, the sentiment labels, with the matrix using data frame function. Well, similarly, we skipped all the text preprocessing steps for testing 1, and we directly use the testing step 6, the already cleaned corpus, and similarly using the weight TF-IDF as the weighting parameter value, only calculate the normalized TF-IDF values for our terms in testing 1, and the terms are only those 1006 words that are from the training frequent terms. So in order to keep the predictor consistent, we only use those 1006 words. And then let's check the dimension. Well, still got 500 rows and 1006 columns representing the reviews and the frequent terms respectively. And next, similarly, we compose a testing data frame using data frame to attach the labels, a sentiment label to the matrix. And let's check the top 20 words. The top 20 words with highest TF-IDF weights. Well, we no longer see the movie. Oh, they're here, but they're no longer on the in the top on the top. So we got action, family, life, real, good, bad. These words are now have the highest TF-IDF values. This is the purpose of TF-IDF. They will like weight down the frequent terms such as film, movie, but they will promote those rare words, rare terms. And similarly, we will create the testing 2 data frame with the similar steps. And here's the top 20 words for testing 2. You can see alien, life, action, love. Those words are actually have the highest TF-IDF weights. Well, next we will use the sentiment classification models with normalized TF-IDF weights as predictor values used for like those 1006 frequent terms as predictors. And we first will compute the decision tree. And well, it will also take a few seconds. So let's directly look at the results. So sorry. So we will use the training. So here. So for the testing data 1, the accuracy is over 64%. And for the testing data 2, it's over 65%. So actually using the normalized TF-IDF weights instead of binary weights, we don't see like much differences in model performance, in decision tree model performance in terms of accuracy. Well, next we can show you the performance when we use a naive Bayesian model. Well, similarly, this model is still built on the 1006 predictors, 1006 frequent terms with TF-IDF, normalized TF-IDF weights as values. So let's generate the model and then evaluate the performance. Actually, like naive Bayes model is should be much quicker than the decision tree model. But let's look at the result directly. So if you still recall, when we use the binary weights as our predictor values, we can reach like more than 75% of accuracy for testing 1, both testing 1 and testing 2. But now for testing 1 and testing 2, when we use normalized TF-IDF weights, we do not outperform the weights. You outperform the models using binary weights. Well, lastly, we also use the kernel support vector machine from Curl Lab. And if you recall, like we can reach 80%, above 80% for everything for our support vector machine model. But here, for testing 1, the accuracy is only 70, almost 77%, and for testing 2, it's still like 76%. So basically, for the kernel support vector machine models, also didn't outperform the support vector machine models using binary weights we built before. Well, these are the approach, the routines when we want to calculate the normalized TF-IDF model. Sorry, TF-IDF bits. But if we want to calculate the unnormalized TF-IDF weights, well, the calculating process will not be in the document term matrix function, but we will introduce you to a new function. Well, first of all, here we will use this document term matrix function to calculate the actual term frequency, unnormalized term frequency. So here we do not include any additional parameter. We just include the cleaned corpus, step 6, and then we remove those terms, sparse terms, and keep those frequent terms. We will still got those exact same 1006 terms, frequent terms. Well, next we will calculate the unnormalized TF-IDF as weights for our predictors. So here is the 1006 terms with their term frequency, and for the normalized option we select false, so we do not want the normalized TF-IDF. Instead we want unnormalized TF-IDF weights. So therefore we will have the unnormalized TF-IDF weights for these 1006 unfrequent terms. Well, the dimension is still the same, 1000 rows and 1006 columns. Well, the rest of the codes are similar. We want to demonstrate you the top 20 terms with highest unnormalized TF-IDF weights. So here, let's see. Remember, like if you recall, the normalized TF-IDF value is really small. It's like less than 0.005. But here we see it's close. The average of the top 20 terms is close to 1. So here we change the range of from 0 to 1.5. And well, next we will construct our training data frame, and then similarly we use the document term matrix and weight TF-IDF to obtain the unnormalized TF-IDF weights for those 1006 frequent term from training dataset. See here, we include this list dictionary code those to this 1006 frequent term collection, and then we construct the testing data frame also using the data frame function, and then we show you we demonstrate these top 20 terms with highest unnormalized TF-IDF weights in this bar plot. The sequence of the words didn't change much, but the value has changed a lot. Well, similar steps for the testing data too to calculate the unnormalized TF-IDF weights for these 1006 terms. Well, next we will use this unnormalized TF-IDF widths as values for the predictor to predict the sentiment of review sentiments. Well, we will still gonna first use the decision tree model. And let's directly check the results. So in terms of decision tree, well, the performance for testing 1 and testing 2 are similar to the decision tree models use binary weights and also normalized TF-IDF weights as values. But if we're using the still running, but let's check the results. But if we're using the naive Bayesian model and also testing 1, testing 2 as to evaluate, we can see in terms of testing 1, testing 2, it didn't outperform the naive Bayesian model when we used the binary weights as predictor values, but it performed similarly to the naive Bayesian model when we use normalized TF-IDF weights as values. And last but not least, we use kernel support vector machine. And let's check the results. Well, it performs similarly to the, because we reach 80% when we use binary weights as predictor value, but here it is close to 80%, and the rest of them are all like, even though they're not like over 80%, not all over 80%, but they're like close to 80%. So it performs similarly to the support vector machine model using the binary weights as predictor values. But this support vector machine model performs better when we use the normalized TF-IDF weights as predictor values. So this is basically what we cover in this tutorial. See you next time. Bye.